And welcome to the Motivation for Hadoop, Part 1 of the webinar series, Cloudera Essentials for Apache Hadoop. Thank you for joining us. My name is John Zuwanich, Marketing Specialist at Cloudera, and I have the privilege of introducing Cloudera Director of Educational Services, Sarah Sprono. Today's webinar will explore traditional large-scale computing systems, limitations, and alternative approaches, and how Apache Hadoop addresses particular issues. We'll reserve some time at the end of today's webinar to take your questions. You may submit a question at any time using the questions panel on your GoToWebinar console. Take it away, Sarah.
Thank you, John. So today we're going to talk about where Hadoop came from, why we needed a new software solution, and the requirements that went into this, and then we'll talk a little bit about how Hadoop solves those challenges. So we're going to start with what problems existed with the solutions that we had and why we needed something new. Then we'll look at the requirements that went into this new approach and talk about how Hadoop addressed those requirements. Okay, so let's start. So traditional systems, they did a lot of things well, but let's talk about what they did and why they weren't necessarily the solution that addressed some new problem. They were typically designed for processor-bound work, so when you had lots of numbers to crunch. And generally, they had small amounts of data that they were working on, but they did significantly complex processing, so lots of CPU. And over the last couple of decades, a lot of effort was put into making machines more powerful. Individual computers got bigger. They got faster. They got more and faster CPUs, and they got more RAM. But the individual machines were scaling up. All right, so if we believe Moore's law, we understand that processing power is continually doubling. It's getting much faster. And that's great for CPU-intensive work, but even that isn't always adequate. So there were systems that were developed to do more distributed CPU-type efforts. So systems like MPI. So we spread the work. Now we can do even more number crunching. In any distributed system, you have a lot of problems or challenges. One of the biggest ones is that some sort of data exchange, or we need some sort of synchronization between these machines. Let me put it in common terms. You have some friends. We all have friends. And if we have a small group of friends, we can keep up with everything that everyone's doing. So I know everything that's going on in some of my close friends' lives. But think if you had 800 million friends. Now I can't keep up with what each of them are doing. Even 10, 20, 50 friends, I probably can't keep up with everything that's going on in their lives. And the reason is it's that synchronization, it's that data exchange. It becomes a bottleneck. I can't talk to that many people. And we have to understand in computers that finite bandwidth is available, meaning I just can't shove as much data as I might want over the pipe. Other complex issues that arise with distributed systems is this idea of temporal dependencies, or let me just put it this way. Things are happening all the time. And if one machine were to, say, fail or have a problem doing something, for others to know about that or know what to, how to compensate, that becomes very difficult or complicated. Ken Arnold was one of the designers of Corba, a distributed RPC framework. And so he knew a few things about distributed programming. And one thing he was quoted as saying is, failure is the defining difference between distributed and local programming. Failure is what it's about. That's what makes this hard. So we have to spend a lot of our time thinking about what happens if something fails. What if a little bit fails versus the whole thing? And what do we do about it? Now, another issue in distributed systems is the data. Where do you store the data? And typically, it was stored on some sort of centralized set of disks, so something like a SAN or network attached storage. And then at compute time, when you needed to process that data, the data had to get copied to these processing nodes where they were going to get the computation done. That works great if you have a relatively limited amount of data. The fan is perfectly capable of holding a whole lot, but the problem is getting it off and to the compute nodes. We might have some issues. And we are a data-driven world. So data has exploded over the last few years in particular. And nowadays, organizations have these giant volumes of data. And it's not going away. So some examples here, and these numbers are outdated. The last time Facebook announced how much data they had publicly, it was something like 15 petabytes. It's an order of magnitude more than that now. eBay, I know in just one of their Hadoop clusters, they have many petabytes of data. And a lot of organizations are generating new data at a rate that is almost unfathomable, in the terabytes a day. So the data, all this data, is actually our bottleneck. We can't get the data off of a centralized place fast enough to all the compute nodes to be able to process all the data that we want to get processed. So although we have all those CPUs ready to do work, I can't get them work to do. All right, so if you think about a typical disk, like a SATA hard drive, maybe reads about 75 megs a second. So if I wanted to read just 100 gigabytes of data and send that to the processor, that alone would take me 22 minutes. And we're not talking about 100 gigs. We're talking about 100 terabytes or petabytes of data. So we need a new approach. We need to think about not having to push the data at compute time, but maybe having it already there. So let's talk about the requirements for this new approach. What are we going to do if we're going to start over and develop something new? What do we need? Well, one thing we have to think about is failure. And in fact, we know failures are going to happen. Google, who originally developed this, or the idea behind Hadoop, they knew that they were going to develop not just a tiny cluster of a few machines, but thousands, tens of thousands of machines were going to be involved. And if you have some number of machines, let's say even just 100, and each one of those has maybe 10 disks, well, disks have a lot of moving parts. They tend to fail. So at 100 machines, each one with 10 disks, that gives us 1,000 disks. And the mean time between failure, or how often I expect a disk to go bad, is approximately 3 years, or 1,000 days. So 1,000 disks, 1,000 days. On average, I'm going to have a disk loss every day. But that was just 100 computers. So I have to be ready for failures. And as stated here, we want to not only recognize that failures happen, but not have it be devastating, not have it be catastrophic. So if a failure of a component happens, I want it to be a graceful degradation. I want to lose a little bit. So if I lose one of those hard drives, lose 1 out of 100 of my machines, I want to lose 1% of my capability. And I don't want to lose data. So the actual data itself must not be unrecoverable. And when that node comes back online, so maybe I go fix it, get a new disk in there, spin it up, I want to be able to use that machine again. So I want it to be able to rejoin the system, and certainly without having to restart the entire set of machines. I want components to be able to come back in. Now, meanwhile, if we know failures are going to happen or could happen, and really at a pretty drastic rate, thousands of machines, we could have failures pretty often, I need to maintain consistency. So from the end user's perspective, they shouldn't really know anything happened. The outcome of the job gives the same results, whether something failed or not, and they really just don't notice. Now, it might have been 1% slower if one of those nodes did fail during the job, but the results were the same. And am I going to notice 1% of performance differences? Probably not. Okay, another real key requirement that went into this design is scalability. So again, if we think about where Google was coming from, they knew they would not need 10 machines or 100 machines, but maybe tens of thousands. And if you think about that, your set of friends, one friend, maybe even 10 friends, you can keep up with what's going on in their lives, right? But tens of thousands of friends? Now we have problems. So we have to minimize some of the issues, such as synchronizing and having to know everything that's going on with every other node, so that we can get scalability. One thing that Google was thinking about is, all right, if they're going to be spending money on these tens of thousands of commodity machines, I want to get all the sort of bang for my buck. I don't want to have to buy a new machine to get a tiny percentage of the capabilities of that machine. And that sounds silly, right? I buy a machine, I get a machine. But in a lot of traditional systems, you could add machines and get more power up to a point. I could add friends, and I could keep up with what they were doing. But I add enough friends, and I can't. So I don't want to lose the power of the machine. In other words, increasing resources should give me a proportional increase in my load capacity. If I double the machines I have, I want double the storage space, because I just bought new hard drives, and I want double the capability or processing power, because I also bought CPUs with those. Those are some of the requirements that went into a brand new approach. So if we understand now that traditional systems, which had data stored in a centralized place and were designed for a lot of CPU-heavy work, did not solve our problem because we had too much data. The requirements that go into this new approach really boil down to two things. We know failures are going to happen, and we want to be able to scale the number of machines we have proportionally. Or in other words, get linear scalability, double the machines, double the power. Okay, so now enter Hadoop. Let's talk about how Hadoop addressed those challenges with traditional systems and addresses all the requirements for this new approach. A little history here. Hadoop is actually based on work that came out of Google. So in the early 2000s, Google was developing a new way of handling what they were trying to do. And as we all know, they were crawling the internet, the web, which was growing at a tremendous rate. So they knew they had to keep up with the volume of data. But they also needed to process all that data, because they needed to crawl these web pages and then index them and run other algorithms over them. So the system that they came up with, they published a paper describing, and that was the Google File System and MapReduce. Those two papers came out in 2003, 2004. Well, meanwhile, Doug Cutting over here at Cloudera was at the time at Yahoo, and he saw these papers and realized it addressed what he needed. Because at the time he was trying to also do web searches and indexing of web pages. And he said, aha, this will do it. So this new approach in the Google File System and MapReduce addressed the problems that we just talked about of reliability, because we know we're going to have failures. We want to scale. We need to maintain consistency, etc. It all boils down to one core concept, and that is, instead of trying to store the data centrally, let's distribute the data as it's originally stored. So as it's coming in, let's push it to multiple machines. So push it out there, break it up, send it around. Then those individual machines can all work on the data that they have locally. So they all have hard drives. When we load data, we push that data out to all these various hard drives, and then we tell them to process the data that is on their hard drive. That eliminates our bottleneck of having a finite amount of bandwidth. Now I don't need to transfer a lot of data over the network. Hadoop provides several core concepts. One is that applications are written in a higher level programming paradigm called MapReduce. It means that as a developer, I get to write my processing my logic, how I want to use this data, without having to worry about things like networking. So I never have to open a socket or know where these machines are or connect around the cluster. I also don't have to care about failures. So as the machines may go down, as a developer, nothing changes from my perspective. My code, if something was running on that machine that failed, that code would get rerun somewhere else for me. Now, another core concept that's critical to Hadoop is that the nodes must talk to each other as little as possible. Going back to the idea of you can have a few friends, right? But you have hundreds, thousands of friends, and you just can't keep up with them. So we'll say, don't bother. Take the opposite approach of saying, you do not need to know what they are doing. You will not talk to each one of those very much. So it's truly a shared nothing. Now, there are times when the nodes do know about each other, but it's, as stated here, as little as possible so that we can scale. Again, going back to one of the requirements that we wanted for this new approach was that I want to be able to double the machines and double the storage capacity and processing power. Not get a little bit more, but get double, and into the thousands of nodes. Now, Cloudera has many customers with hundreds, thousands of nodes in their Hadoop clusters. Okay, a third tenet here is that the data is spread amongst those machines in advance. So again, when you load it, at that time, your data will get kind of broken into chunks, sent around to machines, machines that have capacity, wherever those are. And we need to make sure that the data is safe, even if we have failures. So the data gets replicated. So as it's loaded, it's not only distributed or broken up into pieces and sent around, but even each one of those pieces is then stored 3 times. And that's a configurable number, but the default replication factor is everything is stored 3 times. And that might seem like a lot. That's overkill, right? Why isn't 2 enough? Because we all agree that 1's not enough. I could lose that 1. But 2 is really not enough either at the scale that we're potentially talking about. Now, you might not need thousands of machines in your Hadoop cluster today. Maybe you need a few, but you could grow, and Hadoop allows those clusters to grow into the thousands of machines or thousands of nodes. And at that number, the chance of 2 machines going down before the admin got a chance to come in and fix one, well, now it could happen. So we found that 3 is a nice number. It gives us enough safety, and we don't have to get a page in the middle of the night and run to the data center and fix that machine. We can breathe easy and fix the nodes that fail on our own time. Okay, so the 10,000-foot view of how this works is that when you load the data, you'll load large files, typically. So I might have gigabyte files that were generated from my web servers, maybe they're logs, or from sensors. This data is coming off of various network sensors or something. And you'll typically have these large files that you load into the Hadoop cluster. I said they get broken into chunks. We call those blocks, but they have nothing to do with the blocks on, say, a typical file system. Like, if I'm running a Windows machine with an NTFS file system, those have the idea of blocks, but they're tiny. These are often 64 megs or 128 megs. Now, that seems to be a nice number. So what we're doing is, if you have a gigabyte-sized file, or bigger, if we didn't break it into chunks at all, if we just took that large multi-gigabyte file and put it someplace, then I don't get real great distribution of my data and parallelization of my work. On the other hand, if I took that file and broke it into a whole lot of teeny tiny blocks and sent those around, well, now I have extra coordination and scheduling work to do to coordinate these lots of teeny tiny blocks. So we found that 128 megs, or the default's actually 64 megs, that seems to be a good number. It allows us to break the file into reasonably sized pieces or units of work, spread those around. Remember that they get replicated. So each one will have 3 copies. And then when we go to schedule the work, we'll have these things called map tasks. And that's the first part of the map reduce paradigm. And the map tasks will each work on one of those portions of data, one of those blocks. So I've now allowed myself to distribute the processing into 128 meg units of work. There is a master, and the master is the one who's coordinating some of this the scheduling. Now the masters in Hadoop are not involved in a lot of the activity. We need to make sure that they're not the bottleneck, but they do some kinds of coordination. And in this case, the master allocates which machine should run one of these map tasks. So out of my, say, 100 machines, the data had been spread across them, and a particular block lives on 3 of those. There's 3 copies. So the master will usually pick one of those 3 who has that block to work on that block. We want data to happen, or we want the work to happen on data that is local. Now, I've got all these machines. They can all work in parallel, each one just working on their chunk of the data. Meanwhile, we know nodes can fail. 100 nodes or machines with 10 disks each, that's 1,000 disks. Average mean time between failure, I'm going to have a disk go every day. So we know they're going to happen. The master will detect that. So that it detects that because the worker nodes are just checking in occasionally and saying, I'm here. And when they don't, then the master assumes that they're failed. And it will just reassign whatever work that one node was doing, the one failed one, to another system. Restarting that task is very easy. It doesn't require that I communicate with all the other nodes. So again, coming back to, if you had thousands of friends, you couldn't keep up with them. Well, here we don't need to. If one goes down, we'll just restart what it was doing, and nobody needs to know or be updated or affected. Now, if that failed node were to restart, it can automatically be added back to the system and assign new work to do. Now, there's one potential problem, though. If we have all these hard drives, all these moving parts, when a hard drive goes bad, it doesn't necessarily just go kaput. It might actually start acting slow. And that could be a potential problem here if my 99 out of 100 machines are all fine. But one of them is just ridiculously slow because of some bad hardware or something that's failing. Then that 1% of my work just isn't finishing. I don't wait on that forever. So the master will notice if one machine is actually finishing this task significantly longer time than the others on average. So it kind of watches how fast these tasks are typically finishing. And if one is extra slow, it can start what that node was doing on another machine. So I can do another instance of that same task. And at that point, we're in a race. And whoever finishes first will use those results. And we can kill off the one that doesn't finish. That's a neat feature of Hadoop that allows for these potential situations where you have something like a machine that is significantly slower than others. So I hope that gives you a good introduction to where Hadoop came from. The problems with traditional systems, not that they were bad, not that they had problems inherently, but that they weren't well suited to this data-driven world. And then the requirements that went into our new approach, which boil down to mostly failures can happen, and we want to scale with more machines. And then finally, how Hadoop begins to do that. I would now like to open it up for some questions and answers. All right, so I'm just going to take a look at the questions that came in here. There was a question about how do I learn Hadoop? And that's a very interesting one because being a complicated distributed system, it can be a little bit intimidating. So there are lots of resources available. On Cloudera's website, we have many videos to watch. We have constant blog posts and other resources. We also offer training classes. We have training classes for developers or system administrators or analysts or managers. And then, of course, there's some wonderful books out there like Tom White's Hadoop Definitive Guide. There was a question that came in about data redundancy. And so let me just address how that data redundancy happens. Hadoop is basically doing a redundancy at a macro level. So it is copying data from multiple machines, which is great. If you were to address data redundancy or data safety at an individual machine, you would probably use something like RAID. And what that would give you is redundancy amongst your disks. But it doesn't help you if you were to lose that entire machine and all of its disks. So what Hadoop does, and what we suggest, is you don't need RAID on the individual machines. You let Hadoop do the redundancy. That gives you actually two benefits. One is the data safety. But also, you get the benefit of, now that we have multiple copies of that data, when we need to go process the data, the master who's scheduling where the work should happen, where those map tasks get done, the scheduler now has multiple choices about where to schedule the data, or schedule the work to be done on that data. And it can pick one of those machines that has that copy and maybe isn't busy doing other things. By having more choices there, it can schedule more of those tasks to be run locally, and we get what we call better locality, or in other words, we read more of our data locally. There was a question about what if a master fails? So that's a very interesting question, and up until very recently, if the master went down, your Hadoop cluster was unavailable. So in other words, it's sort of a single point of failure. It wasn't a major problem because for most people, they use Hadoop as a batch processing system. And if your batch processing is down for 10 minutes, you might not care. Bring it back up, do your batch processing at the top of the hour. That said, we understand that for some customers, it is a problem. And so one of the things that Cloudera has been spending a lot of engineering effort on recently, over the last many months, was making this master highly available. So in our upcoming release of Cloudera's distribution, including Apache Hadoop, we now have a highly available name node and highly available job tracker. There was a question about running Hadoop on virtual servers. So that question can be interpreted a few different ways, but let me address it this way. Whether or not companies choose to virtualize is really up to them, and I understand that there are benefits to a company when that's their standard. Let's say they like to roll out software by having these virtual instances or images that have been approved by IT and whatnot. It can also give you potentially some highly available benefits. That said, you need to be a little bit careful. You would not want to run multiple nodes on one physical server in Hadoop, because that would actually lose some of the benefits that Hadoop is doing for you, such as the data redundancy. But if it's a one-to-one, one virtual server on one physical server, then that will work fine. We just want to ask that you do the performance benchmarks, because every once in a while that it can have a significant performance impact. All right, let me look at the other questions here. Lots of questions. There was an example of, there was a question about what is a typical task in Hadoop? You know, I mentioned these map tasks. Well, what is a map task? The kinds of processing that people do in Hadoop, again, are often batch processing work. So I use Google as the example because they came up with the original design for what became Hadoop. But when most people think of Google, they think of a Google search. And if you go to google.com and enter a search and click enter or I'm feeling lucky, it comes back instantly, right? So fast. That's what Google's good at. That is not kicking off a MapReduce job. Instead, the MapReduce job is done ahead of time. So they go and crawl these pages, and they use MapReduce to index them and come up with, they run algorithms over them and rank these pages to build these indexes, and then the indexes actually fuel the searches. Now they store the indexes in something called Bigtable, and Hadoop has an equivalent of that called HBase. HBase sits on top of Hadoop and can respond to very low latency requests for key value pairs. So the typical work that people are doing in Hadoop, one is indexing. The other is you can do things like build recommendations from the activity that you see your customers doing. So you might have your web logs. Maybe you have your web logs and you have your point of sale records, you know, the purchases. And you might want to go through those with maybe some machine learning code, like a collaborative filter. Collaborative filter is really just a fancy term for building recommendations or coming up with recommendations. And you scan through that data, each of these map tasks, all scanning their bits of it, and building recommendations so that you can suggest, you know, the right products to the right kind of customer that's viewing your site. Other things that people are doing are graph analysis. So if you think of social graphs, like Facebook or LinkedIn, both of those sites suggest people you might know. And the way they do it is by treating all of their users, all of their customers or friends, as nodes in a graph. And they have connections to others, which are just edges of the graph. And they use this MapReduce where each task gets some tiny bit of that graph. And they build graph analysis. They have algorithms that they run over this to determine, you know, if Jane is friends with Bob and Bob is friends with Tom, maybe Jane should know Tom. All right, so those are a few examples. Let's see, other questions. And I'm sorry, I'm not able to address every question. I'm just going to pick out a few here. Another question was, somebody had heard that MapReduce is very complex, and is there a programming abstraction over it? And I would absolutely agree that MapReduce is complex. It's actually not that hard to learn what a map is and what a reduce is. They're actually quite simple. But because they're so simple, they're sometimes difficult to put into practice. And the reason they had to be that simple, and therefore a little bit hard to use, is to get the design requirements that we just talked about. We need fault tolerance, scalability, and consistency. And the only way to really do it was to make this MapReduce paradigm kind of very basic in what it does. That means that to do these graph analysis or complicated machine learning algorithms, you often need to come up with brand new algorithms that work with MapReduce. That's actually one of the motivations behind a project called Mahout that is included in Cloudera's distribution of Hadoop. And Mahout is a set of packages that provide these machine learning implementations like collaborative filtering or clustering algorithms, but implementing them in a way that they apply to MapReduce. So sometimes you need to come up with new algorithms. Sometimes you need to take a real sophisticated programmer who knows algorithms to be able to write the MapReduce. And that is the motivation for higher level languages, as the person asking the question suggests. These higher level abstractions do exist. So I like to think of, a computer has assembly code. but I don't write assembly code. That's what languages like Java and C are there for. If you think of MapReduce as the assembly code, there are tools called Hive and Pig that are the higher level languages. And they will translate their language into MapReduce. Hive borrows from SQL, so it looks like the structured query language where you write select and from, where, group by, order by, and it will turn that into MapReduce. Pig looks more like a scripting language. It's a data flow language where you describe how you want the data to go through a set of transformations, and again, it will turn that into MapReduce. All right, let me look back at those questions. Okay, there's another question about how does Hadoop work with existing file types? For example, types that came out of SQL or relational databases. Few ways. So if you have relational databases, you might have Oracle, MySQL, Netezza, Teradata, etc. There is a tool called Scoop. Like these other tools, it's included in Cloudera's distribution of Hadoop. And Scoop is meant to extract rows out of your tables and put them into files in Hadoop, because Hadoop is just files. And that's a nice benefit, that the data in Hadoop doesn't have to be extremely structured. A lot of data out there is more complex. It might just be text or web logs or binary data. But if the data is in a structured form in a SQL database, then we can use Scoop to load those records into files in Hadoop. Hadoop can also read really any file format you have. If it's not a file format that Hadoop natively understands, for example, text and various kinds of text like comma-separated values or XML, JSON, and let's say it was something really proprietary, special to you, then you can actually write the little parsing logic for how Hadoop reads the file. And it's just an extensible class that you're allowed to add, and then it will use your parsing logic when reading your data. Okay, another question. How do I get my data into a Hadoop cluster? What technologies exist to load data into Hadoop? There are several tools to help you with it. So first of all, you can do it kind of by hand. There is a shell command where you can run Hadoop fs put. So I'm putting into the Hadoop file system. And that just starts doing a distributed copy to these nodes. So you could have cron jobs that regularly grab files from your systems and put those into the Hadoop cluster. There are also tools to help you do this in more of an automated fashion or a highly available fashion. And those, the one I mentioned, Scoop, helps you if your data is coming from a relational database. There's another tool called Flume, and Flume, F-L-U-M-E, Flume is designed for real-time collection and aggregation of data and loading it into Hadoop. One of the most common use cases for Flume would be weblog. So on each of your web servers, you run a Flume agent, and then they will collect the weblog events, possibly aggregate those, because we don't really want to put tiny files into Hadoop. We want to aggregate them into bigger files, and then load those files into Hadoop for you. Flume also has some nice advantages of giving you some reliability guarantees and high availability of that data loading. All right, other questions? I'm sorry I'm not going to get to all these questions. There was a question related to, so if I have all these nodes, hundreds or thousands of nodes, meaning servers, how do you manage them? And there's several tools that people do. So I mean, you can do it by hand, but SSHing around your cluster and trying to keep all these config files in sync is a real headache. Some people use tools like Chef or Puppet. We also have a tool called Cloudera Manager, and there's a free edition of Cloudera Manager up to 50 nodes, and then beyond that, the full edition is available with Cloudera Enterprise subscription. But Cloudera Manager will take care of not just making sure the config files are in sync, but everything related to installing and managing a Hadoop cluster. So I definitely recommend you check that out. There's some questions about compression, so let me address those all together. You can certainly use compression along with Hadoop in a couple of ways. So one, your data can just be compressed. You'd want to follow some of our tips on how to do that appropriately, because if you just take a large file and gzip it and put it in Hadoop, then we have a problem breaking up our processing work into units. Because we can certainly spread the data around, we can still do that, but if I take a big gzipped file and I try to peer into just the middle of it, I can't decompress it. I actually need to read it from top to bottom to be able to decompress gzip. That's the way the gzip algorithm works. So we wouldn't want you to do it that way. But with our techniques, and we have several, one of the best is to use a indexed LZO library that Cloudera contributes to, and that allows the compressed file to still be splittable into units of work. So that's one way you can use compression. Another way is the analysis job itself can be told to use compression whenever it has to store intermediate results. And that's just a simple configuration option for a job when it's running. There was a question about, can I have multiple jobs running concurrently? You can. Now there's a couple of complexities to that. First is, do you have the capacity to run multiple jobs at once? So your administrators will configure each particular machine, each node, to be able to run some number of tasks at once. So if you think about it, it's often, you look at how many cores, CPU cores the machine has, and you'll say, I can run that many tasks because I can do that much work in parallel. So if there's enough capacity across the cluster that we could schedule more tasks than we are running at the moment, then Hadoop can certainly do that. There's some other complexities there, though. Sometimes you want to control the priority of jobs. Certain jobs might have an SLA where they have to finish in 1 minute, 10 minutes, hour, whatever it might be. And so there's a couple of scheduling techniques or schedulers that your admins can configure Hadoop to use. One is called the fair scheduler, where it lets you set up these different queues and allow a fair usage of the Hadoop cluster amongst users. And that way you can give them priorities and such forth. Another question is, how do you figure out how many nodes you'll need for a particular use case? And I'll say that it definitely does depend on the use case. But the general rule of thumb that works out pretty well for most customers is you can base your capacity planning around your data volume. So we tend to buy machines or servers that are have fairly large disk capacity. So you might maximize how much disk you can put in a machine, and then buy more machines for the amount of data that you need to store. The reason that works out pretty well is if you follow some of our standard advice, and you can find this on our website or at your favorite vendor's website. For example, if you typically buy from Dell, you can look at their reference architecture for Hadoop that was designed in conjunction with Cloudera. And those typical reference architectures will say, for these many hard drives, you want these many CPUs and this much RAM. And there's nice little formulas. So as you add machines, you get the extra disks, but you also get the CPU and RAM. So we find that it works out pretty well if I base my calculations around how much data I plan to have and then how fast that data is going to grow. There's another question about running Hadoop in the cloud, and we see this kind of question a lot. It might have something to do with the fact that cloud is in our company name. But to be honest, most people actually don't run in a what it might be called a cloud. They often run Hadoop on bare metal in a data center. It doesn't have to be that way. You know, there are people that like to use cloud services, you know, maybe Amazon or others. The trade-off there is just whether or not, you know, you have to do your own analysis. Which one is more cost-effective for you? If you're going to use a cloud service all the time, sort of you know, constantly, then it might be cheaper to go buy your own machine. If you're going to use it here and there, maybe that's the better way to go. You also have to look at trade-offs of disk latency. You know, are you getting local disk, or is it potentially not necessarily local disk? But it really does depend. There are people that are doing it. The bulk of our customers are actually running in their own data center on their own hardware. Okay, there were several questions that were all related to the major use cases of Hadoop, and I talked about some of them. You know, graph processing like LinkedIn, Facebook, and others are doing with social data. There's also the product recommendations that I mentioned are a major use case, and that applies not just to product recommendations, but ad recommendations, music recommendations, so people like Pandora, Last.fm that are, you know, suggesting music for you, or Netflix, which is suggesting, you know, movies that you should listen to. There are other examples that are commonly used with Hadoop, and one is just a more typical ETL kind of process. So you need to transform your data in some way. So you extract it from the systems that it starts in, put it into Hadoop, do transformations, just regular data cleansing, or get your data structured. If it's unstructured or complicated to begin with, or possibly dirty, run it through transformation. Now that it is structured, maybe it's destined for another system. So an often common pipeline we see is data starts in OLTP, relational databases, and web servers, and who knows what else. First place it gets aggregated to is Hadoop. And in Hadoop, we join it, we clean it, we structure some of it, we build recommendations, and then it's destined for, or parts of it might be destined for your enterprise data warehouse. Parts might be destined to go back to your relational database, and some might stay in Hadoop. Another question is, I heard Hadoop's file system is immutable, and that's actually true. The Hadoop distributed file system is a sort of write-only or append-only file system. So you can add files, and you can add two files, but you can't actually change some records in an existing file. If you really wanted to, what you do is you read it and write out a new one. So the question asks, then how is Google saving its index? And how this works is Google or others that are indexing data are reading the raw data in Hadoop. They are then building the indexes. They might be storing those indexes in HDFS in the Hadoop file system. Or there are other places that Hadoop can write directly to, like HBase. So it can be storing data directly to HBase. Then, if it needs to allow really fast access, you probably wouldn't leave it in HDFS. You would use either HBase or take that data and load it, say, back to a relational database. And Scoop can go both ways. So Scoop could load or extract the data from your relational database into Hadoop, and it can go back from Hadoop to a relational database. Okay, I'll take one last question. There's a question about, can I integrate with the PHP language? And I'll broaden that to say, what languages you can use. So this MapReduce higher level language allows you to write your processing in nearly any language. Now, Hadoop itself is written in Java. So Java is sort of the primary language for writing MapReduce. But you can also use something called Hadoop streaming to allow you to write your data analysis in PHP or Perl or Python or Ruby, really any language that can read from standard in and write back out to standard out, which gives you nearly anything. You could write your data analysis in R. The trick is that whatever language you use, you are always reading or getting or working on a small portion of the data. So each map task is reading one chunk of the data. And you can't coordinate with the other map tasks that are running. In fact, you don't even know what order those are going to run or when they're going to run. So you have to do or think through your analysis, your logic, on what you can do with just a few records that you're looking at. So as long as you can come up with the algorithm, you can write it in nearly any language.
This concludes today's webinar. Thank you, Sarah, and all who attended. If you missed any part of today's presentation, it'll be available online soon. Part 2 of Cloudera's Essentials for Apache Hadoop, Dissecting the Apache Hadoop Stack, will take place March 30th. Please look for an announcement with registration information from Cloudera, which will be coming soon. Thank you.